We will now begin our discussion on fast algorithms for computing isosurfaces. Recall that we were discussing isosurface extraction as one of the ways of visualizing scalar fields. So in the 2D case, we had an isocontour that was defined as the pre-image of a scalar value. So if you had something like an elevation map as shown here, one way to visualize the elevation or the terrain is by drawing a collection of curves where each curve represents a set of points that have a given elevation. This idea extends very well to 3D, where the isosurface now is a collection of points that forms a surface, and it is essentially the pre-image of a scalar value. We talked about marching cubes algorithm and its natural variants, the marching squares in 2D and the variant for linear interpolants, that is marching tetrahedra and marching triangles, are very popular algorithms for extracting isosurfaces. We talked about the marching cubes algorithm in the previous lecture. The same algorithm essentially works for 2D and in the linear interpolant cases. If you already saw this video, then you essentially got some idea about how the algorithm proceeds by looking at the voxels one after the other, extracting the isosurface within the voxel and moving forward. Hence the term marching cubes. So in this lecture, I'm going to discuss efficient algorithms for isosurface extraction. The way we will bring about efficiency in the algorithm is by talking about variants of the marching cubes. So the algorithms that we will discuss today and in the two subsequent lectures can be broadly categorized into cell search methods and contour propagation methods. Today we will talk about two types of cell search methods, one that searches the domain and the other that searches the range. And in subsequent lectures we will talk about yet another algorithm that uses the range search paradigm and contour propagation. The reading for the search methods, the cell search methods, are this paper by Livnath called Noise and a paper by Signoni et al. Both papers are already uploaded onto the class notebook. We will now look at the domain search methods and this specific range search method called Noise. So let's try to understand what cell search really means. So what is an isosurface cell? It is essentially the voxel or the three-dimensional cell that contains an isosurface. Now, if I look at the values of the scalar field at every vertex, let's say this is vertex v1, and so you have a value here which is f of v1, f of v0, and so on. We have 8 vertices, so you have 8 different scalar values. I can talk about the minimum of this scalar values and the maximum of the scalar values. If the iso value lies between the minimum of all f v sub i's among these 8 vertices and the max of all f of v sub i's, then we know that the cell contains the isosurface. The reason we know this is because of our underlying assumption of a bi or in 3-dimension tri-linear interpollant. This follows essentially from the mean value theorem. So now the Marching Cubes algorithm essentially searches through all these cells, looking at them one by one. It uses the min and the max values to determine if that particular cell contains the isosurface. If yes, we know how it uses the lookup table to extract the isosurface. In today's class, we will focus on this search step. So we already discussed during our discussion session that this linear search may not be very efficient. And the reason is as follows. Given an iso value, typically, as in for a typical data set, only a small fraction of the 3-dimensional cells or voxels contain the isosurface. So for example, if I have a volume with n cross n cross n cells, so n cubed cells, the average number of isosurface cells, as in the average number of cells that contain the isosurface, is is n square. The argument here is follows from, like I mentioned during the discussion earlier, this number n squared follows from the ratio of surface versus volume argument. So this number was also empirically verified in a paper by Carr et al. On histograms and isosurface statistics. I have included the link to the paper here. In case you are interested, you can look at the slides and get the paper. So let's state formally the problem of efficient isosurface cell search. Once we have solved this, we have a fast Marching Cubes algorithm. So I'm given a scalar field, and this field is defined on a cube grid with n cells. So this should be C1, C2, Cn. With min max ranges A1, B1, A2, B2, and so on, An, Bn. So these are the n cells. The requirement is to identify isosurface cells. So the requirement is to find all cells C sub I such that A sub I less than C less than B sub I. Right? So I hope this is clear. So let's say you have have a cube whose function values here are decided by the values at the 8 vertices. So this cell, let's say, has 8 vertices, and this cell has a corresponding min-max range, which can be written as A sub I, B sub I. And we call this an isosurface cell if the iso value C lies within this interval A sub I, B sub I. So the question is, how do I find such intervals quickly? The first strategy we will employ is domain search via subdivision. So next we will apply the same method on the range space. So this is going to be, the domain search is going to be a straightforward application of the octree that we saw while talking about hidden surface removal. So the idea, if you recall, is to subdivide the entire space into subdomains using axis parallel splits. So let's say that we have a square grid. So this is a 2D illustration, and the isocontour is as shown here. How do I identify the cells that contain this isocontour? I would begin by subdividing my space into subdomains using axis parallel splits. So if you recall, the quadtree splits the domain into 4 subdomains, and in 3D the octree subdivides it into 8. What I would like to do is to annotate this octree or quadtree by storing the min and max values corresponding to each subdomain. So these min and max values can be aggregated over all cells in the subdomain to give us a single min max value for the subdomain. So now if the min max interval does not contain my iso value, I can skip an entire subdomain. That is the strategy. If it does contain, then we recursively traverse the subdomain to identify the cell. This is the idea. So here is the recursive subdivision followed by yet another recursion. So the tree would look like this. I would start with the root, which corresponds to the entire domain. So note that there is a min max stored at the root. I check if C is contained within this min max interval. Let's say yes. So I traverse the subdomains recursively. I look at all 4 subdomains and I check their min max. Now the min max corresponding to the so this is number 1, let's say 2, 3 and 4. So subdomains 2, 3 and 4 do not contain the iso value. So that is already going to be clear because we see the isocontour in this case. So I would not traverse those subdomains, whereas I do traverse one recursively. Now again, 1 has 4 children. I would recurse to only one of them, as we can see, until I go and identify the one cell that contains the isocontour. And when I do this, I stop. Now, when I identify the cell containing the isocontour, I use the lookup table to extract the isocontour and display it. So if K, so I introduced these terms earlier, but let me talk about them again. If K is the number of cells that contain the isosurface, so this is the number of isosurface cells, and n is the input size, the number of voxels, then it's easy to see here that the runtime complexity of this algorithm is O of k log n. To identify each cell so each one of the k cells that contain the isosurface, I would have to traverse the depth of this tree, which could be log n. This is already a good algorithm. K is inevitable. We have to necessarily look at all k cells that contain the isosurface. Now, of course, there is the log n factor. Log n could be large. Now, even if it is a factor of 10, then this could seriously hit the runtime performance. Let's see if we can improve this. One important observation is that our search is dependent more on the min-max intervals rather than the domain. The isosurface could be located anywhere in the spatial domain. We do not want this to affect our runtime performance. We would like it to depend more on the min-max ranges. So the idea is to design an algorithm that searches in the range space. So what does this mean? Let's look at all the ranges A sub I, B sub i's and plot them here. So what you have here is a particular interval A sub I, B sub I. All the intervals are shown here along the real line. There is the global minimum and the global maximum identified as well. And here is my ISO value. The idea is to hierarchically subdivide these intervals based on the min-max ranges, right? So let's say I subdivide the real line into 2. So this partitions the set of intervals, may not be into equal halves, but it just partitions. I could hierarchically partition the intervals such as this to get 4 collections of intervals and then 8 and so on, and use this hierarchical subdivision to search for the set of intervals that contain my ISO value. So in this figure, we are essentially trying to report all the intervals that intersect this line that indicates the ISO value. Now clearly, the hierarchical subdivision is not going to do a good job always. For example, there can be more than one cell within each of my intervals. So the subintervals between the two dashed lines could contain multiple A sub I, B sub I intervals, multiple cells. One way to search through these cells is to sort the intervals A sub I, B sub I that are contained within that subinterval. So the question is, how do I sort them? What is the sort index? Well, I could use the min values to sort or the max values to sort, or use both. So let's say I sort all the intervals once with respect to the max value and once with respect to the min value. Now let's say I have identified the subinterval. So note that we had the real line and we had identified a subinterval that contains the ISO value. And this subinterval could have multiple intervals such as this. So now I have sorted all these intervals based on their max values and again based on the min values. Given an ISO value, I could identify G1 and G2, which is the set of all, G1 is the set of all intervals whose max is greater than or equal to the ISO value. So here both both of these so in both cases the intervals are sorted in increasing order of the max and in increasing order of the min. So we want to report all the intervals whose max is greater than the ISO value, which is shown here. And when we look at the min array, we want to report all the intervals whose min is smaller than the ISO value. Let's call this G2. What we want to report is the set of intervals that lie in both arrays. So G1 intersect with G2. This is what we would like to report. Now, of course, things are not going to be as clean as what I showed them to be. In most cases, we are not going to be able to get a clean subdivision of the range. So for example, here we have a subdivision using dashed lines, and none of the subintervals here contain a clean set of intervals. So many of these intervals cross these subintervals. So it seems difficult to design an optimal algorithm because this subdivision does not seem to work. Often the first step towards the design of a fast algorithm or a good algorithm is a useful and good representation of the data. So this works in our case as well. So the key idea is to represent each cell, which is each voxel, as a point in 2D rather than an interval. So each interval, each min-max interval is now represented as a point in 2D. So the two axes here are the min and max axes, and we call this the span space. So I'll let you take a minute to think about which of these two plots could represent a collection of cells in the span space. If you think about it, max has to be greater than min. So all the cells have to appear as points above the x equal to y line. Where are the isosurface cells going to be? So in the span space, let's look at an iso value C. So here is the iso value C. This is a point in the x equal to y line. So which cells, so each of these points here corresponds to a particular isosurface cell. That is the representation. Let's remember that. So this cell has a interval min max, and we are representing that as a point in the span space. Now, which cells contain this iso value C? So the min has to be less than C. So this corresponds to a half plane. So all points to the left of this vertical line satisfy that condition. Similarly, max has to be greater than C. So this corresponds to, let me not draw that fully, the half plane given by this horizontal line. So all points above this horizontal line satisfy that condition. So the set of all points that lie in the intersection of these two half planes are the cells that we need. So these are essentially the points that belong to this open-ended rectangle. So the blue rectangle is our query. We would like to find all points that lie within the blue rectangle. So note that the blue rectangle is defined by this iso value C. This is called a range query. So how do I search for the isosurface cells? I call what is called a range query in 2D space. Range queries are studied extensively in computational geometry, and there are very efficient algorithms available here. So far, we have not yet seen how this new representation simplifies our search. It seems to be intuitive that the search corresponds to a range query, but how has it simplified our search? The key insight is that subdividing space, such as the plane, is easier because of this point representation, as compared to subdividing the set of all intervals. So this is the idea behind the noise algorithm. The noise algorithm proposes the use of a subdivision that is called the KD tree. The KD tree is a generalization of the octree or the quad tree that we have seen. It is an extension of this data structure in two ways. One is it extends the data structure to higher dimensions, or it extends this, to be more specific, it extends this subdivision technique to higher dimensions. More importantly, KD tree is a generalization of the octree in the sense that it partitions the set of points into equal halves at every level in the tree. So it partitions the data first of all by alternating between the dimensions at each level of the tree. So let's understand this KD tree first. So here is a set of points. We will restrict our attention to the span space. So I have the black points. The KD tree is shown on the right. So we begin by partitioning the set of points using a vertical line. So note that the vertical line corresponds to the min axis. So this is the first partition. I partition using the median point along the x-axis. So I choose the median with respect to the x-axis or the x-coordinate, and so this essentially partitions the set of points into two, the ones that go to the left and the ones that go to the right. Next, at the next level, I partition recursively, but now using the max coordinate. So now I would use the median with respect to the max coordinate and partition. So this will give me these horizontal lines. So now with this, I have divided the set of all points into 4 parts, equal parts. And we then proceed by again choosing the min axis and max axis and so on. The KD tree extends to higher dimensions where you alternate between all the dimensions. So you would go with respect to the x-axis first, then the y, and then if there is a third axis, then the z, and so on, and then come back to x. Here we have essentially a 2D tree. This is a two-dimensional case. So this k is used again, but from now on, whenever we talk about KDT, the k there refers to the dimension. There is another k that we use for the number of isosurface cells. Hopefully that will not be confusing. The context will tell us what we are talking about. So this is the KD tree. Similar to the octree or the quad tree, this can be constructed very efficiently. Finding the median can be efficient. You may have seen a linear time algorithm for computing the median. So there are efficient algorithms for constructing the KD tree and for querying the KD tree. How do we use it here? That is also quite simple. You essentially just traverse the tree recursively. So let's look at two cases. First, ISO value is less than the min, right? So I have an ISO value which is less than the min at the root. So what does this mean? So this means that so this is min. So my ISO value is, this is min, shown using the red arrow. My ISO value is less than the this min. So it lies somewhere here, right? So what this means is that my query rectangle is going to be completely lying to the left of the vertical line corresponding to min. So what this means is that the right subtree is not going to contain any isosurface cell. So I can ignore the right subtree and recurse onto the left subtree. Right, okay. Now, what about the other case where my iso value is greater than the min? So, the greater than the roots min. In this case, note that there are many isosurface cells both in the left subtree and in the right subtree that could contain the iso value. So I would have to recurse through both the left subtree and the right subtree. Let's look at this algorithm again. The first case, like I said, is when the iso value is less than the roots min. So we had the x equal to y line, and we had the line corresponding to the root. This is the root dot min, and I know that my iso value is less than this min, right? So it's clear that I have to focus my attention on the points that lie here. I do not need to recurse on the right subtree, because the right subtree contains isosurface cells whose min is greater than the iso value. So none of those cells will contain the iso value. In the second case, what we had was we had the and now our iso value was greater than the root min, right? So it lied somewhere here. So this meant that the query rectangle is something like that. So I would have to traverse both the left subtree and the right subtree. In both cases, I do have to look at the interval corresponding to the root. This is constant time, so not an issue. So the question now is, what is the running time for this query? So this is not your usual recursion, right? Because at least in one of the cases, it seems like you have to traverse both subtrees. The key observation here is that so in the first in case, of course, you traverse only one subtree, so that's fine. So the second case, I would like you to look at this more carefully. One can show that if you skip one level, so of course in this level you are looking both at the left and right subtree, but if you go to the next level, one can show that you look only at 2 out of the 4 subtrees recursively. So what this means is that your recursion now, the recursion is of the form T of n is 2t out of the 4 children 2 levels down, you look only at 2 of the children and recurse. And of course, there is some constant work in addition to that. Well, actually, this is not constant. If you look at it more carefully, there will be some additional work here. but all of them will add up to k. So, so this requires some thinking. If you take an example, then you will be able to figure out. So this case is easy. The next case you will be able to figure out, and if you look at it carefully, you will be able to show that out of the 4 children, one level down, you will have to recursively look at 2 of the subtrees. The other 2 subtrees you can either ignore completely, as in you can show that those subtrees will not contain any isosurface cell, or you can show that those subtrees can be written down as is, so as containing isosurface cells. So either the subtree does not contain any isosurface cell, or all the nodes in that subtree are isosurface cells. I will let you work this out. Right. So essentially you get this recurrence T of n equal to 2Tn over 4, and this results in the worst case running time of O of under root n and a k. So of course n is here the number of input cells, k is the number of isosurface cells, so that is the size of the output. So compared to the previous runtime, which was k log n, this is much better, especially because we know that k is often n to the 2 over 3. So I will stop with this description of the noise algorithm. In the next lecture, we will talk about an improvement of this runtime.